Hello, this is a demonstration of a simple flow prediction using GRU as the neural network predictor. This is an overview of the total application. We are using data from the Cognite data platform. From this we have collected historical data with these tags. The data belongs to a first stage scrubber, and we are trying to estimate the flow based on these variables. For this we are using TensorFlow and Keras to train and create the model. It is based on GRU, gated recurrent unit, and we have these layers. The first is 32 nodes, the second is 16, the last is 8, and then a final linear layer for the output. Yes, the first thing is we need some additional libraries, so we import these. We need matplotlib for plotting, we need TensorFlow as the backend for the neural network, NumPy and pandas used for the data, matrix operations, and pandas is also used for the data frames, which we use to treat the data in. We also have Seaborn for additional plotting. We have OOS because we have defined the API key as a system variable. We need to get that into Python. We use DIL to save objects, mainly the scalar objects in this case, so that we can load them again in the real-time application later on. We also use sklearn to create the scalar. Then we have TensorFlow. Here we have the model structure. We have importing layers. We have importing the callbacks, for example, for early stopping and so on, so that we can stop the training when there is no improvement to avoid overfitting. And then we import the optimizer. Then we have some of the Cognite imports. This function is used to get all the data in one core. And then we have to configure the session. We also need to have some date time for plot. Then different versions of the libraries presented. And then we have the function that is responsible for getting the data from Cognite. This is all the tags defined above. And here we have a fixed date time in order to make collecting the data at a later time easier. If you use days, this would sliding every day, so we could get different results if you trained it tomorrow. Then we get the data. Then we have some data processing after we have gotten the data. This function handles that. It splits the data into training and test set. Then we scale the data, and then we save the scalar objects and return the scale data. Then we have the function for training the neural network. Here we define the future steps to estimate. Find how much of the data is training data. We define the batch size, the sequence length, how many epochs you want to train for, and how many steps per epoch you want to train for. We create the model, create the batches, we add the layers together, we define the optimizer, and print out a summary of the model. And then we define all the callbacks, and we train the data, and we load the best weights from the checkpoint. Because one of the callbacks will save when there is a best fit to the validation data, and this is loaded then after the training is finished, so that we get the best estimated model for the validation set out. Then this is the batch generator. It simply generates random batches from the given batch size, sequence length, and train length, and outputs these. Then we have some model conversion. As it is batch training, it is stateless. It expects to have many values to predict at once. And every time you call the predict function, it won't save the last state of the network. This converting it to this way will have it do that so that we can use it in a real-time application when we want to estimate at every time step. Then a simple function for saving the model is made, as we need to get this model for estimation in the real-time application. We have a simple correlation plot to see if the data is correlated or not. That's all the functions. Now to the main program. First, the data is downloaded for Cognite using the function defined above. Then we have some interpolation of the data. Even though the data is interpolated in Cognite, it sometimes contains nonce. So I have an outlier function here which we did some tests with, but we found that it was not needed for the dataset that we are using here in that time frame. Then we remove the timestamp from the data because we should train with that. This is for interpolating after we have done the outlier removal to replace those with none and then interpolate again. Then we see the shape of the data set. We are doing some plotting here just to see that we have gotten all the variables. The same here. This is tail, last of the data. When we plot the data, we see that for this 0 to 100 is realistic. This 15 to 45 is realistic, etc. We see nothing unreasonable here. This was also checked with Stig Harald, which knows a bit about the process. Then we have the correlation plot. Which just checks if everything is correlated. So if it's very blue, it's very correlated. Here you see that they are very correlated with each other. And yeah, this was just used for reference to see if there was some relations in the data. Then we train the network. Here we see the summary of the model. Here we see the summary of the training. In this case, we see that it's early stopping and that here while loss is improved. This is the last validation improved and it's saved to a checkpoint. After it tries for sometimes, then it hits the callback to reduce the learning rate. It reduces the learning rate to try and make a better model. It didn't work, so we have early stopping after a couple of more failures to improve. Then we print available history data. Then we plot validation loss versus training loss, and we see here that validation is a little worse than training. Of course, because the model is trained on the training data and would give a better fit here normally. I think around here was the last save, and this is the lowest point in the validation data. So it makes sense. And this is very important to avoid overfitting and underfitting. So you would have another relationship between validation and training with epochs. Then the model is saved. You see it's successful. Then we plot the models. We plot the estimation and the real data on the training data. It's a slightly less variance, little offset. We just might have been unlucky with that little piece of data. Then we see the validation data against the real measurement. See here, it actually gives a better fit than the training data in this case. It's a lower variation and seems that it follows the trend of the data. Gives a reasonable fit. That was that. Now I want to show you the real-time application. The model is saved to disk. These saved models are copied to the same directory as the lab view file. They are here. also the objects used for scaling that I showed you earlier. And we can simply open this VI. Simply uses Python 3.6, gets the data from a small Python script, then it predicts the data from the same Python script. These are just functions in the script. This is just to make sure that we are using the same file path that these are in, that the VI is in actually. Then we have 5 seconds for the sampling time. Then we can try to predict some data. Just run it a bit earlier. As the model is now stateless, it starts with the last trained states. So this has to converge to the value. It takes some time before this warm period is done, and the network manages to predict proper values. This takes some time at first start. There. First value from Cognite in and first prediction in. So it starts here, because this is the last train state. It quickly converges to the model. It flattens against the graph. And these are predicted values without the input, without the output in the input. So these are just using other sensors to predict what this sensor is giving out. Thank you.